Howdy folks. This lesson will focus on the uses and limitations of descriptive observational studies of human thinking and behavior, how we gather the data, and how the data can be accurately interpreted. Again, with the larger goal of giving you the proper tools to understand what research reports really mean. So when we talk about descriptive studies, what we are talking about is the first step in psychological research. That is, observing the way people naturally behave without us doing any manipulation of any variables. I'll tell you about three major categories of descriptive studies: case studies, surveys, and naturalistic observation. Recall that descriptive studies allow us to uncover patterns of behavior that help us 1. Find correlational, not cause-effect, relationships between variables, and 2. Generate testable hypotheses to design later experimental studies that can tell us whether the correlational pattern has a cause-effect basis. So one of the most valuable features of descriptive studies is their ability to detect reliable patterns in human thinking and behavior as it naturally occurs. This is especially important when the variables we are interested in are ones we can't manipulate in an experiment, either because a variable simply can't be experimentally manipulated, for example, people's sexual preferences, IQ, or religious beliefs, or because it would be unethical to manipulate the variable, for example, people's recreational drug use, or whether parents mistreat or abuse their children. Have a look at this graph. These are true descriptive data that psychological researchers have observed in a natural environment. The graph shows that parents spend about 4 times more time explaining science concepts to their boy children versus their girl children. We've also observed that school teachers tend to spend more time explaining science to boy students than girl students, and that there are more men than women employed in high-level science-based jobs. So there is a correlation between the amount of time adults spend teaching boys versus girls about science and the success of men versus women in the science field. But what does that correlation mean? Well, since it's a correlation, we cannot conclude cause and effect, but we can generate hypotheses about it. One obvious explanation would be that the more science training as kids causes better science ability in adults. We could test that, but I hope you can see that would be a little iffy, because it would be unethical to intentionally deprive some kids of good science training. Instead, we observe the success of boys we know got more science attention in school and compare it to the success of girls we know got less science attention in school. So if we do that over and over for different schools and find the same pattern of results, does that make it cause and effect? No. And this is where hearing correlational outcomes can really trip you up. It makes a lot of sense that more training would cause more success. And it's reliable because we see it over and over. But we're still only observing that pattern in different natural environments. So note here that this would be an example of the naturalistic observation type of descriptive study. But we're not manipulating any of the variables. Therefore, this kind of study is not an experiment, and therefore we cannot conclude cause and effect. Sometimes with humans, there are simply things we cannot ethically manipulate, but we can still use the patterns to raise awareness and help create new policies to try to alter the patterns. And an example of this is the new Women in STEM National Science Initiative, which tries to equalize science training for girls and women compared to men and boys. So now let's talk about the case study type of descriptive study. In the case study, scientists study one individual person in great detail. This is an extremely useful method when studying folks with brain injuries, because we can test them in lots of different ways to see what things they can still do and what things they can no longer do now that some part of their brain is damaged. This gives us lots of data to generate hypotheses about what the damaged part of the brain was responsible for before it was injured. Of course, this is still a descriptive study in which we are not manipulating anything to experimentally damage parts of people's brains would be completely unethical. So the data we collect from these case studies are only correlational. We cannot legitimately say, for instance, well, Phineas Gage's frontal lobes were badly damaged in his railroad accident, and since then, his personality has changed completely. Therefore, the frontal lobes must control personality. That would be a wrong conclusion for two reasons. One, we didn't manipulate the variable of brain damage. We just observed brain damage that had already happened. And two, we would be generalizing one person's experience to say that the whole human population would have the same experience with the same damage. And I'll explain in a moment why it's incorrect to generalize from a case study. But again, we can use descriptive case studies to generate theories to explain the pattern and hypotheses, if ethical, to test the pattern for cause and effect. Fortunately, technology has given us new tools for studying the brain without damaging it. One particularly fun and useful new technology is called TMS, transcranial magnetic stimulation, in which we can temporarily paralyze a specific part of the brain in a healthy subject, thereby mimicking brain damage, and then test what functions they lose. There is no damage or after effect for the subject, so it's ethical. Furthermore, because we can use this technique to experimentally manipulate the part of the brain we disable, and we can test lots of different people using this exact same manipulation on this exact same part of the brain, now we can conclude cause and effect, and we can generalize the results to the rest of the population. That is, now we can take observational data from case studies like Phineas Gage's and use it to generate hypotheses about what a particular kind of brain damage is responsible for, and then use TMS on healthy brains to test whether that observational pattern holds up in the experimental method. Cool, right? You can watch a demo of TMS on a healthy patient at the URL shown here, and this URL is also provided for you on our eCampus page just below this lecture link. Is the survey, and this is the one you're probably the most familiar with. We take surveys all the time for fun, like on Facebook. Hopefully you were also able to do the pre-screening for your SONA credits, and that'd be another example of the survey method. Surveys simply ask people to self-report their own information. Again, notice, we're not manipulating anything here. We're just asking people to answer questions that give us data we can use to look for patterns that naturally occur. So along with all the other uses we've discussed for observational data, surveys have a couple of extra advantages. First, surveys can usually be done anonymously, so people are more comfortable answering personal questions such as about drug use or sexual preferences. Second, you can create one survey and give it to as many people as you want, so you can collect information from tons of people, which greatly increases your ability to detect reliable patterns of thinking and behavior that are already occurring. Moreover, by gathering data from a lot of people, you greatly increase the representativeness of your sample. That is, the more people you include, the more likely you are to get data from all the different kinds of people in the whole population, such as both men and women, people from different cultural backgrounds, different socioeconomic backgrounds, different religions, and so on. This is called a representative sample because it means your study includes information from a sample of people who represent all the kinds of people in the population whose information you don't have. In other words, the people giving you information in your study represent other people like them who are not giving you information in your study. And why is a representative sample so important? Well, take a look at this chart. If we want to generalize our findings to a whole population of people, like yourself, then we have to do everything we can to make sure that every kind of person, like yourself, from that population is fairly represented in the sample of people we actually test. So this is one of the main reasons why we cannot generalize case studies to the population. Case study is just one person, so they cannot represent a population. Now, that said, I want you to know we can never be certain that our sample represents every possible kind of person in the population. So in science, we use a statistical correction formula to allow for the possibility, always assuming that we have missed at least one kind of person. So we adjust our outcomes to correct for that possibility. You don't need to learn how to mathematically perform that adjustment in this course, thank goodness, but I want you to know the rule exists so that you can have more confidence that research outcomes from real scientific studies are generalizable and include you. One more important thing to note about samples and generalizability is that we can restrict our sample's representativeness as long as we also restrict the sample's generalizability. So it's important for you to know when you're listening to research outcomes what the sample consisted of. What kind of people? So, for instance, a researcher may only be interested in bilingual women's language ability. In that case, the research could test a sample of a bunch of bilingual women and then generalize the results to the population of bilingual women. If you're not a bilingual woman, then those outcomes don't apply to you. They don't generalize to you. As long as the sample fairly represents the population of interest, then generalizability to that population is appropriate. Thanks and gig 'em.